All right, so let's continue with our development of these questions of material symmetry and or material isotropy. So here's how far we've got, right? We have said that we are considering rigid motions on omega naught. And these motions are of a type that carry the reference configuration to a new reference configuration. Okay, C belongs to R3 and the usual stuff. All right, now we have our strain energy density function, which for hyperelastic materials is a function of F, right? So the question we have arrived at is the following, which is, the question is, how is psi of F related to psi of F star, right? Where F star is the deformation from this new reference configuration, right? And we saw that F star is F Q transpose. Okay? All right, so really the question is, how are these two related? Okay, how is psi of F related to psi of F star? Okay? All right, so the statement of material isotropy is the following. Material isotropy is assured if this function psi that we have picked is such that it doesn't care. Okay? So material isotropy is the requirement that psi is a function such that psi of F equals psi of F star, which we know is psi of F Q transpose for any rotation. Okay? For any rotation. So what it is saying is that the material that makes up this ellipsoid is such that it doesn't matter how you rotate the material, how you rotate the reference configuration, right, before presenting it to the deformation. Okay? All right, so if you were to cut out a little piece of this material, right, as small as you like, okay, I've cut out a little piece. Now, it does not matter whether I present the piece the way it was oriented when I pulled it out of the material and then stretched it out in this direction, or if I took this little piece, rotated it arbitrarily, and then applied the same deformation relative to the walls of the room. Okay? What it is saying is that the strain energy density function of this material is such that the orientation of the microstructure does not matter. The material is invariant to rotations. It's invariant to directions of the microstructure. Okay? All right, so we call this material isotropic. Okay? So what we're saying is strain energy density function is invariant to rotations on the reference configuration right? Consequently, if it's invariant to rotations on the reference configuration, what it is saying is that it's invariant to orientation of the microstructure. Okay? Invariant to orientation okay. So if I may show you things pictorially, it is the following. You have omega naught, right? We pick a little neighborhood, okay, and suppose we see that the microstructure has that orientation, okay. Pull out that little piece of microstructure, pull out that little neighborhood, okay. That is my neighborhood now. It does not matter whether we maintain the same orientation of that neighborhood and subject it to a deformation that is fixed with respect to the walls of the room, or that is fixed because of the experimental equipment you're using, okay? Or if before we apply this deformation, we first do a rotation, right? We do a rotation where now the planes are the planes or the microstructure or the fiber or whatever you want to think about, right, has a different orientation relative to the same deformation. Observe that F is still defined the same way relative to my basis E1, E2, E3. These are the walls of your room. This represents your experimental equipment. Okay? That is still going to stretch the material the same way relative to ambient space, but not relative to the microstructure of the material, right? Clearly, what these fibers here are experiencing because of their orientation is different from what the fiber here is experiencing is different from the stretch that fiber is experiencing, sorry, right? Okay, even though relative to the walls of the room, my F is the same. Okay, so for this little piece here, this little piece experiences F Q transpose. This little piece here experiences F. Okay? However, if psi is such that it does not matter, psi of F, the energy stored in this case, is the same as the energy stored in this case. Okay? If they are the same, what it is saying is that the fiber orientation doesn't matter, the microstructural orientation doesn't matter. You may even go as far as to say that there is no microstructure to the material. Okay? For mechanical purposes, there is no microstructure to the material. Okay? Now, this is saying something special about the function psi. Okay? Because this has to hold for all Q. Okay, in particular, we're saying that psi, the function, is invariant to Q. Okay? Right, and because psi is the only thing we have to represent the mechanical response of the material's mechanical response is indeed isotropic. It is independent of direction. Okay, so this is our statement of material isotropy. Okay? Okay, so this is our statement. So we are saying that the material is isotropic. Okay. In the context of symmetry, we say that the material possesses the full symmetry of SO3. Okay, material is isotropic. It possesses full symmetry with respect to WRT SO3 or SO3 plus, strictly speaking. Okay, it's rotationally invariant. Number of ways of saying it, same thing. Okay, the material is rotationally invariant. Okay.